Hey guys, I thought I'd just do a recap of what we did yesterday, since it's all parametrics, which is what we've already talked about. It's just the way the AP asks it. Sometimes it's a little different. So some of these things aren't even in our book. So I'm going to go ahead and just go through it from start to finish. Again, especially since several of you were out yesterday, I thought this might help. And even if you were here, it might not hurt to get a little refresher, especially when we get to Part D, because I think a lot of people had trouble with Part D when we were trying to do it in class. So I'm going to definitely do that. So first things first, let's look at what we've got. We've got a curve defined parametrically. In fact, they're giving us dx dt and dy dt right from the start. And a couple of initial conditions here and restrictions. And then it says, please find the acceleration vector at time equals 2. Alright, so clearly that is something different. We've never had to put it in that form. The good news is it's just a different notation. So if this is our dx dt and our dy dt, our position vector is literally just x of t and y of t. Okay, I don't know what that is at the moment, but I'm just saying in general. The position vector, and it's noted with this type of, bracketry, whatever you want to call it. It's not, it's not a parentheses. It's not a squigglies. It's basically a less than and greater than, but it's representative of the vector notation. So this is the position vector. Well, then our velocity vector would simply be the derivative of the x component and the derivative of the y component. And there's your velocity vector. It's actually that simple. You're literally doing each component, each part individually. Okay? So now, velocity, don't mix up the velocity vector with dy dx. Dy dx was when we did dy dt divided by dx dt and so on and so forth. This is a little different. This is literally defining it by component. Okay? So then, of course, the acceleration vector, this is velocity, which is s prime. I was just about to write it again. So acceleration is the derivative of velocity, which is the second derivative of position, and that would be my x double prime of t, y double prime of t. So when they ask us in that, in that other question, find the acceleration vector for time equals 2, and I look at what we've got, well, technically they're already giving us this. We know the velocity vector because they gave us dx dt and dy dt. That's x prime and y prime. So my acceleration vector would be the derivative of my velocity vector, so derivative of dx dt. So that's going to be negative sine t cubed with a chain rule kicker, comma, derivative of my dy dt is going to be 3 cosine t squared times the chain rule kicker. And there's my velocity vector. And all I need to do now is apply, I think they said when t equals 2. So a of 2 would be negative sine of 8 times 12, and then 3 cosine of 4 times 4. Put that in your calculator, and you should be able to get that. Let's see. Let me grab my calculator one sec. All right, got it. So, excuse me. Let's see. Can you see that all right? I think that's okay. So let's see. Let me first make sure I'm in radians. Of course not, because my last video was geometry. So radians, and let's see. Negative sine 8 times 12. Negative 11.872 and then 3 cosine 4 times 4 is negative 7.8437. There's my end bracket, and that is part 1, part A. Okay, so again, it's just a notation thing, and it's just a matter of knowing which sort of level you're on, just like we did way back in the day. Okay, all right, now let's look at B. B asks us to find the speed of the object at time equals 2. Okay, the speed is just a different way of asking something we kind of already talked about. So let's see, let's do this. Let's keep that up there. Speed. Let's just look at a generic old curve, and let's focus in on a particular point. Well, at that point, my dx dt is acting on this point horizontally. So this this point is moving at some rate horizontally. That's my dx dt. This point is also moving at some rate vertically. That's my dy dt. So if we're talking about vectors, we're talking about a resultant vector, where if I bring my dy dt over, I have a resultant vector that is determining exactly what direction this particle is going and at what rate. So I really want this. I'll call that ds dt. Well, you probably can see it already. For those of you that were here, you already know this, but for those of you that weren't here, you probably see already we have a right triangle, and we could basically just use our Pythagorean theorem. So ds dt is going to be the square root of dx dt squared plus dy dt squared. And if that looks familiar, it should, because this is how we developed our arc length formula. Except I don't want all these little segments added up. I just want this one. Speed is the magnitude of the velocity vector. And all that basically means is I need this length. Okay? If I have my velocity vector, I need this length to get my speed. Okay? So this is your speed. Okay? So if I look at the problem at hand, to get my speed, I'm literally just going to do exactly what it says. Cosine t cubed squared plus 3 sine t squared squared, and that's my speed. And I believe, was it also t equals 2? Let me just double check. Yeah, t equals 2. So I'm going to put in 2 and hope for the best. So this is going to be cosine 8 squared plus, let's see, this is going to be 9 sine of 4, but it's really sine squared of 4. And this is really cosine squared of 8. So let's get the calculator and check that out. We've got the square root of cosine 8 squared plus 9 sine 4 squared, which is about 2.2751, I guess. And there's your speed. Okay? So speed is I know it looks like it's just arc length, and it has that feel to it, because this would just be one of those segments. But that's actually all I need, is that one particular segment at that one moment in time. I'm not adding up all the segments that make up the whole curve. Okay? So there's your speed. I'm actually going to stop the video now, and just because it's getting on like the 8-minute mark, and then I'll go and do parts C and D in the next video. Okay? So here we go.